Before we discuss the angular momentum of a rigid body about an axis, let's start by considering the angular momentum of a particle about an axis. Okay, we will consider the simplest case. Here's our particle, here's our axis. Let's just draw in this radial line from the particle perpendicular to the axis. Let's assume that the particle's velocity is in a circle, so that every instant the velocity vector is perpendicular to the position vector. Okay, so here's the position vector. So the velocity vector might look something like this, but actually that it looks like it's within the plane of the screen. So okay, the axis is within the plane of the screen, so the velocity vector will be into the screen. And these two are always at right angles. Now we could consider a more general case, of course. We could consider the angular momentum of this mass m about this axis when its velocity is in any direction and where r is constantly changing in magnitude. But we will be looking at a rigid body, so r will be always fixed in magnitude because the particles are at a fixed distance from each other in a rigid body, and the velocity vector will always be perpendicular to this position vector r. So again, you've got to imagine particle m moving into the screen with velocity vector v. So here's the definition of the angular momentum. Actually, it's the magnitude of the angular momentum, because angular momentum is actually a vector. Now, we will not discuss the vector nature of angular momentum. We will just consider the magnitude. So we just take the momentum of the mass m, which is its mass times its speed. Again, we're just looking at the magnitude. That's v without the arrow. Okay, so mv is the magnitude of the particle's momentum at this instant. And we multiply by the perpendicular distance of the particle to the axis. Now the particle is moving in a circular motion, and we can relate the speed v of the particle, that's the magnitude of the velocity, to the angular velocity omega. So from circular motion we know that the speed v of a particle moving uniformly on a circle is the angular speed r omega times the radius r. So the magnitude of the angular momentum, or we will just refer to it from now on as just the angular momentum, is m times omega r times r. Okay, so I plug omega r in for v, so we get m times omega r squared. Now we can deal with the case of a rigid body rotating about an axis. The magnitude of the angular momentum of a rigid body about an axis is I times omega, where I is the moment of inertia of the body about this axis, and omega is its angular speed. Now let's pick a particle that makes up this rigid body. Let's say its mass is delta mi. Whenever you see the Greek letter delta, you know that we're talking about a particle that makes up the body. So this particle has a very, very small mass, tiny mass. Let's say its distance from the axis of rotation is r sub I. So we're dealing with the ith particle. Okay, so I is a subscript that runs from 1 up to whatever number of particles make up this body. It could be billions or trillions of particles. So we try to make delta mi as small as possible. Okay, so now this distance ri is the perpendicular distance of the particle to the axis of rotation. The particle is moving with circular motion. It has got some speed that we could call vi. Now we know how to get the angular momentum of this particle about the axis. We multiply the mass by omega by the distance squared. Okay, so just to repeat what we saw earlier, we take the momentum of this particle, which is delta mi times v. Well, it's actually the magnitude of the momentum of the particle. To get the angular momentum, we multiply this momentum by ri, and we saw that vi is just omega r. Okay, v is omega r for a particle moving with constant speed in a circle. A very important point here is that omega does not depend on the particle. Omega is the same for all the particles. The angle swept out in unit time for all the particles is the same. So whether we're talking about this particle or a particle that's further out, say this one here, its distance from the axis is greater, omega is the same. And it's the same for this particle here, which is much closer to the axis. Now the speeds vi will be different for all these particles, because vi is proportional to r. If we double the distance of the particle to the axis, we double the speed of the particle. But the angular speed is constant. It's the same for all the particles that make up this object. Okay, so that's just the angular momentum of one particle. Well, more accurately, it's actually the magnitude of the angular momentum, but we won't keep saying the magnitude of the angular momentum. We'll just say the angular momentum, meaning that we are talking about the magnitude of the angular momentum of the particle. So, to get the angular momentum of the entire rigid body, we sum the angular momenta of all the particles that make up the rigid body. So I've put in the summation sign to indicate that we're summing all of these over I. So I ranges from 1 up to some extremely large number. Okay, that's the total number of particles that make up the body. We try to make delta mi as small as possible. So we're summing over I. So this omega is just a constant. It just appears in all these momenta terms. So we can take it outside the summation sign. And notice what we're left with. This quantity here we've seen before. It's the sum of the products of all the masses of the particles with the square of the distance to the axis. That's known as the moment of inertia of the entire body about this particular axis. Of course, it depends on the axis that we are talking about. Angular momentum only makes sense with reference to a particular axis. We can't just say the angular momentum of the body in general. We have to refer to a particular axis. It depends on the axis. For a different axis, we'll have a different angular momentum. So this derivation was really more of an aside. You just need to remember that the angular momentum is given by I times omega. Analogous to Newton's second law of motion for a moving particle, we have the principle of angular momentum for a rotating body. I'll start off by just stating this principle, and then I'll go through it in detail. The rate of change of the angular momentum of a rigid body rotating about a fixed axis equals the moment about that axis of the external forces acting on the body. Now, the right hand side of this equation could be rewritten as equals external torques acting on the body. So we saw in the section on statics that the moment of a force about an axis is known as the torque, is known as a torque. Okay, so I'll keep using this terminology. I'll keep referring to the moments of the forces as torques from now on. Okay, so let's try to understand this principle. I'm going to consider the right hand side of this equation, the torques acting on the body. So here we have a rigid body that's constrained to only rotate about this axis. It cannot rotate about any other axis. It may already be rotating with angular speed omega, or it may not be rotating. It could be just stationary, sitting here, waiting for an external torque to act on this body. So what is an external torque? Well, an external torque involves an external force on the body. We are not going to talk about internal forces. Internal forces are the forces between the particles that make up the body. So, molecular forces and so on, electrical forces, whatever. We're not interested in that. All the bodies, this is a rigid body, so internal forces don't come into this picture. Let's consider an external force on this body that creates a torque. Now, I could imagine an external force acting along this axis of rotation. Well, that will not create any torque. That will not cause the body to rotate about this axis. Remember, the body can only rotate about this axis. It can't rotate any other way. So this will only cause the body to be displaced downwards. So, and similarly, if we have an external force acting parallel to this axis, this external force will not create any torque about this axis. It won't have the effect of rotating the body about this axis. So the external forces must not be parallel to this axis. Okay, so let's imagine an external force acting here. Now, obviously I'm trying to show this picture in 2 dimensions. It's meant to be a 3-dimensional object. So this force here you've got to imagine is into the screen. But we now have an external torque acting on the body. So let's suppose that this force has magnitude F. How do we get the torque about this axis? So we covered all this in the section on statics. What we do is we consider the line of action of this force F. So they extend on the force F like this and behind here as well. And we get the perpendicular distance of the line of action of F to this axis. So let's imagine that the perpendicular distance is here. So I'm indicating that this distance is the perpendicular distance. Of course, in other situations, the perpendicular distance might be over here somewhere. So that's why we have to extend this vector, so we can indicate that perpendicular distance. I'll just put it here. There's our right angle. Let's suppose that the perpendicular distance is R. To get the magnitude of this torque, we write down the magnitude of F times the distance R. We multiply these. Now, we could imagine many torques acting on this body, not just this one that I'm showing you. We could have a torque that causes the body to speed up in its rotation, or to start rotating if it wasn't rotating to begin with. Well, it might be this force here into the screen. Okay, so if it had angular speed omega, if we apply this external torque, we could call this torque L. If we apply this external torque L, it will cause the body to speed up. Or if we could imagine a torque applied to the left of this axis. So if the body was already rotating with angular speed omega in this direction, if we apply a torque to the left of the axis, it will cause the body to slow down. We need to consider the possibility that there are more than one torques acting on the body. So imagine several forces acting on the body, F1, F2, etc. F is the resultant of those forces acting on the body. We would have to apply the principle of moments to get the torque of the resultant force acting on the body. So that's something we saw in the statics section. So as a reminder, the principle of moments tells us that the moment of the resultant force F on the body is the sum of the moments of all the constituent forces acting on the body. So using that principle, we will be able to get the position of the resultant force vector acting on the body. So knowing its position, we can get its distance to the axis of rotation. And from that, we can get the magnitude of the resultant external torque in the body. So we'll denote that by L. Okay, so that's the right hand side of this equation. What about the left hand side? We have to consider the rate of change of the angular momentum. So we want the rate of change of this quantity here. So how is Iw changing with time, or I omega changing with time? So we differentiate it with respect to time. Now we have a product of two things here, a product of I and omega. Now, what can we say about I? Well, I is the moment of inertia of the body. That does not change. So as a reminder, I'll write it over here. I is the sum of the products of all the masses that make up the body and the distances of those masses to the axis. Square of the distance. This does not change unless the particles move around within the body, and that's not going to happen because we have a rigid body. So this quantity is fixed for the body. Never changes, it's constant. So I is just a number. So when we differentiate a number times a quantity, we can just take that number out and differentiate omega with respect to time. So I is a number. It could be 5, it could be 6, it could be anything. Okay, so the rate of change of I omega with respect to time is I times the rate of change of omega with respect to time. Now this quantity could change. Omega doesn't have to be constant. If we apply an external force to the body, omega could increase or decrease. If the body was at rest to begin with, well, applying an external torque will cause omega to go from 0 to some new value. So we can now write down the principle of moments. L is the sum of all the torques, well, the magnitude of the sum of all the external torques. That's equal to I times the omega dt. Now this looks like Newton's second law for the motion of a particle, F equals ma, where F is the magnitude of the resultant force on a particle and A is the magnitude of the acceleration of the particle. M is the mass of the particle. You can see the similarity. Well, you'll see it more clearly now in a few seconds because I'm going to rewrite the omega dt. So omega, remember, is the rate of change of the angle with time. Okay, it's the angle swept out in unit time. So we can write down d omega dt in terms of theta. So we differentiate this with respect to time. It's the rate of change of omega with respect to time. But that's just a second derivative of theta with respect to time. Now another way to write the derivative of a quantity with respect to time is to put a dot over the quantity. That indicates we're differentiating with respect to time. So if we're differentiating twice with respect to time, we have theta double dot here. So we can write this as L equals I times theta double dot. Now let's go back to Newton's second law for the motion of a particle. Well, x is the displacement of the particle. So A is just the second derivative of the displacement. Okay, so v, the speed, is equal to x dot. So if we differentiate the speed with respect to time, we get the acceleration. Okay, so we're differentiating the distance twice with respect to time, like we differentiated the angle twice with respect to time to get the omega dt over here. So we have F equals m times x double dot. So theta double dot plays the role of x double dot in Newton's second law. I, the moment of inertia, plays the role of the mass of a particle in Newton's second law, and L, the magnitude of the sum of the external torques on the rotating object, plays the role of F, the magnitude of the resultant force on a particle. Now we saw in a previous video that if we set F equal to 0, we get Newton's first law. So as a reminder, if 0 equals m times x double dot, okay, if the resultant force on an object is 0, well, it tells us that x dot is a constant. The v is constant. It doesn't change with time. Because if we differentiate v with time, we get x double dot. We get the acceleration. And if that derivative is 0, well, the speed must be constant. Actually, the velocity is also constant. If we look at the vector form of Newton's second law, not only the speed but the velocity is constant. So we get Newton's first law. If the velocity is constant, we have that the particle moves in straight line with constant speed forever, if no external forces act. So this is Newton's first law. And we have an equivalent form of that for a rotating body. So if we set L equal to 0, so no external torques act on the body, we get 0 equals I times theta double dot. So just like here, where v is constant, well, v is just x dot. The speed, the derivative of distance with respect to time. So over here we see that theta dot is constant. But theta dot is just omega. Okay, the rate of change of angle with respect to time. So omega will be constant if no external forces act on the body. So in other words, if this body was rotating to begin with, and no forces were acting, no external forces were acting on it. So if we imagine that this body starts off with this rotation omega, well, provided no forces act on this body will keep on rotating with angular speed omega forever, provided no by forces I don't mean a force acting along this axis. If a force acts along this axis, it won't affect rotation. The body will rotate forever. But this force has no torque. The perpendicular distance to the axis is 0. So if no torques act, this body will rotate forever with angular speed omega. So that's like the equivalent of Newton's first law, but for a rotating body. Finally, as an aside, we will consider a derivation of the principle of angular momentum for the very simple case of a system that consists of just one particle of mass m. So we will consider the angular momentum of this system, that is just this particle of mass m, about this fixed axis. So let's suppose that the perpendicular distance of m to the axis is r. Suppose initially, for simplicity, that there are no forces acting on m, so m is just sitting here. Now imagine a force F applied to m, so this is our resultant force on the system. It's the only force acting, so it's the resultant force. So that'll give us a resultant torque on the system. Now I've said system a few times, but the system is really just this one particle. Imagine that F acts for a very short interval of time. Let's suppose that that interval of time is delta t. So the particle will move in a straight line distance in the direction of this force. So we'll assume that this force is constant over this very short interval of time, delta t. So the particle moves from here to here. Now the distance from here to here is so small that this distance here is also r. And let's suppose that this angle swept out is delta theta. Let's suppose that the distance travelled by the particle is delta x. Now, we can approximate delta x by the arc of a circle of radius r, the arc of a sector of a circle of radius r and angle delta theta. So the sector would look like this. Radius r, angle delta theta. So since the angle is in radians, delta theta is in radius, we just multiply r by delta theta. So this is approximately equal to r times delta theta. Okay, that's just the arc of a circle of radius r, angle delta theta. This approximation becomes exact as we let delta t approach 0. Okay, so that's what I'll do now. So this happens over a time interval delta t. So let delta t approach 0. So we can replace the delta t with dt when we take this limit. Okay, so if I go back up here and replace these deltas with d's, this approximate equals becomes equals. Now let's apply Newton's second law to this particle. So F is the resultant force acting on the particle. So we know that the magnitude of the resultant force F is the mass of the particle times the magnitude of the particle's acceleration. So we just take the scalar form of Newton's second law. We'll forget about the vector form. We're not going to worry about the vector form, so I'll leave off those arrows. The acceleration is the magnitude of the resultant force divided by the mass. But we can also look at the acceleration in terms of theta. We can look at it in terms of angular acceleration. So if I divide both sides of this equation by dt, we get dx dt equals r times d theta dt. Of course, d theta dt is just omega. Now imagine differentiating both sides of this with respect to t. So if we differentiate dx dt with respect to t, we get d2x dt2, or the acceleration of the particle. If we differentiate the right hand side, we get the angular acceleration, d2 theta dt2. Now the r is just a constant. Now we're assuming that r remains constant because over a very short distance, very short time interval dt, the particle moves from here to here, but this distance r is really the same as this distance, so r hasn't changed. Okay, so we leave that constant r to one side when we did differentiation. Right, so the left hand side is just a. The second derivative of distance with respect to time is the acceleration. So we can set this thing here equal to f over m. Now let's rearrange this equation. I'll divide both sides by r. I'll take the right hand side here and multiply above and below by r. If I multiply above by r, see the torque is coming into this now. Force times distance. But I must multiply underneath by r to get mr squared. So on top we have the torque. That's denoted by the letter L. Okay, that's the magnitude of the resultant external torques on the system. So the torque only comes about from this force. This is the only force acting on the system. So force multiplied by perpendicular distance of the particle to this axis. By the way, this is a right angle. I should have made it clearer that the angle between force F and this position vector r is 90 degrees. So the torque is just F times r. Now what about the mr squared? Let's consider the moment of inertia of the system. Now the system just consists of this single particle. So to get the moment of inertia, what do? We take its mass and multiply it by the square of its distance to this axis. And if there are more particles, we'd do it for all those other particles and we'd sum them. But we have no sum here because there's only one particle. The moment of inertia of this system is just mr squared. It's just the moment of inertia of this particle. That's all the system is. The moment of inertia is denoted by I. So now you see if we multiply both sides by I, we get L equals I times the angular acceleration, d2 theta dt2. Or we could write it as I times d omega dt. Or indeed sometimes you'll see it written as I times alpha. Sometimes the letter alpha is used for angular acceleration.